All right, we're back with another blog about the moon, and this time it's going to be on tides. Why do we have tides, and why are they caused by the moon? Most people can tell me that tides they're caused by the moon, right? Well, why? Even if I asked what about the moon, people would tell me it's gravity, which is correct, but then what about the sun? Isn't the sun like a lot bigger and thus has a lot more gravity? So why does the moon affect us more than the sun when it comes to tides? Let's take a look. So the moon causes tides because of the moon's differential gravitational force. What? So differential gravitational force? It's not that bad. All it means is that the moon pulls on the Earth differently. So the moon is closer to this side of the Earth right here in the front, right? So it's going to pull on that actually 6% more than the back side of the Earth because it's actually farther away from the moon. Gravity is a force and it acts as you get farther away from it. It doesn't, the strength isn't as strong. So the stuff on the front side of the Earth here gets pulled on the moon 6% more than this side. Now the sun is really far away and it doesn't see us as well. It does have differential gravitational force, but it basically treats the Earth as a point source, not completely. That's how we get spring and neap tides. I'm not going to go into that, maybe in another blog. But the sun, because it's so far away, doesn't exhibit as strong of differential gravitational force as the moon does. Because it's so close, the moon can actually treat us like a sphere rather than a point. And that's how we have differential gravitational force. So this is a program that my boss, Dr. Bradstreet, and his best friend, Dr. Stillman, wrote. And it's going to help us understand tides. I can move the moon, I can change its orbit, I can do all kinds of fun stuff. Now, we need to know what the Earth is feeling at any given point on the surface. So to do that, we actually have to first look at the middle. You see here's a vector. A vector is just a force in a direction, and you can see it follows the moon. Kind of cool. So what I'm going to do now is put on what the Earth feels at the different cardinal points. So if you were here on the side closest to the moon, you can see it's a pretty strong force, right? And as I move these around, they follow the moon. Now, looking at this, I would think that this is high tide, that's low tide, and these are like normal tide. And sadly, I'm wrong. This is high tide, that's high tide, this is low tide, and that's low tide. And to understand that, we have to understand what each part of the Earth is actually feeling. To do that, we have to subtract out the middle vector. If you understand math at all, you'd understand this. To understand what this part of the Earth feels compared to this part of the Earth, we have to subtract that out. So let's do that. Let's subtract out that middle piece, and let's make it a little obvious. So there you go. I put in a vector now that's subtracting out the middle. I've canceled out the middle by putting its exact vector on top of him, and then I put that vector on each of the other vectors. So now what is the resultant of this? What is the resulting force? That white arrow is the resulting force. So if I take the red plus the orange, I end up with the white. If I take the red plus the orange, I end up with this little white. If I end up the green plus the orange, I get nothing, which is what we expect. And then you can see here, that's the resultants for the rest of them. Now I'm going to take away everything but the resultants. Now that's pretty cool. So judging by this, I have high tide. I have a high tide that's not as high, but it's a high tide. And then I have low tide and low tide. Let me put some more on. Now here's what's really cool. So you can actually see the ebb and flow of the water. So as the moon goes around us, you can actually see why differential gravitational force makes tides. So this part's feeling a pretty strong tug, and this part's actually feeling a strange tug, and these guys are being pulled in. And that's differential gravitational force in a nutshell. Pretty awesome program, if you ask me. You can see, end of the world, kind of, the moon. That's awesome. So the next time you're at the beach, look for the moon, and you'll be able to tell what tide it is. If you see the moon directly over it doesn't matter what phase it is. It depends on where it is compared to you on the Earth. So if you're looking directly overhead and you see the moon, say you see the first quarter moon and it's over your head, well, that's when the moon is closest to your part of the Earth, when it's due south. So you're gonna have high tide. If you see the moon on the horizon, that's when it's actually not, that's when the moon is moved off and it's at that 90-degree angle, and you're gonna have remember the 2 arrows are pointing in, and that's where low tide was. So when you see the moon on the horizon, you have low tide. If you don't see the moon at all, well, maybe it's directly underneath your feet. and that could be another high tide, but it'd be a little tricky. But if you can see the moon, you can tell, if you see it on the horizon, it's getting higher in the sky, you're going to be going into high tide. That's kind of cool. And if it's above your head and it's starting to go down, then you're going into low tide. Hope you enjoyed the lesson on the tides and differential gravitational force. If you have any questions, let me know. Either feel free to email me, find me on Facebook, any of the different media outlets. And I'll be coming back with a couple more lessons on the moon. The moon is there's a lot of stuff to talk about. So until then, talk to you guys soon. All right, we're black. We're black. We're not back. We're black with another